have some about it. The motion requested me to talk about three-phase systems. So I'll try to go through basics and try to introduce you to the idea of three-phase. What is three-phase? Why we use it? What are the benefits? And some of the other things associated with it. Okay. So we'll start with simple. Maybe like we have taken in 201 about AC circuits or AC. AC generally is a sinusoidal voltage which can be expressed mathematically as something this is the peak value of the voltage, this is the frequency of the voltage, and this is the phase angle of the voltage. If you want to sketch it, it is something like that. This will be theta. This is Vm. And this is the time period for one cycle. It's known as like one cycle. So the time period of one cycle, so from there you find the frequency which is 1 by time period. And the omega is angular frequency which is 2 pi f. The voltage which we use in Saudi Arabia, for example, has f equal to 60. And as a result, omega will be 377. This is single phase voltage. So we are talking about peak value. There is a phase angle. And there is frequency. As a general rule, when you have a electrical supply system or power system in a country, it has same frequency. So omega is basically fixed in Saudi Arabia. So your house, my house, every house has same value of frequency. If you go to another country, they may have a different value. At present in the world, mostly there are two frequencies. Some countries have 50 Hertz and some have 60 Hertz. The main difference is 50 Hertz are those countries which were at some stage colonies of British Empire, like India, Pakistan, other countries. And 60 Hertz are mostly in those countries where American influence was more. Canada, US, Japan, after the World War, and things like that. Okay. There are some differences between 50 and 60, but I think we'll not go into that. The main thing is I want to, so you understand the AC voltage. In AC voltage, we define one quantity which we call RMS value. It's also called effective value. So you need to understand physically what it means. So for example, you have this voltage. If you apply this voltage to a heater or to a lamp or to a resistor, the current will be like that. If the resistance is more than 1. So the voltage is changing, current is changing. And voltage and current are in phase. So if you try to find the power, this is voltage, this is current. Of course, power is voltage multiplied by current. So the power will be something like that. See, negative multiplied by negative is positive. Positive multiplied by positive is positive. So the power is basically varying like that. This is power and this is time. So in one cycle you sort of have two bumps of power. So the question is, I'm saying, what is the value of power? It's not constant, it's changing with time. So what you do is you try to find what is this area. This area gives you energy, which has been given to heater over one cycle. And then if you divide that energy with this time, you get a value which is like that, average value. So that is called RMS value. So mathematically, R is root, mean, square. If you forget what is what is the formula for that, it's very simple. First square root, then mean. Mean is average. Average is basically 1 by time period, integration from 0 to time period. You integrate it and then divide it with the time period. Square. So if it is a voltage, you take the square of the voltage. So this is VRMS. So the root mean square value, basically mathematically calculated like that. Well, it is mathematics, but I'm saying you said, doctor, you mentioned that you'll give us the physical meaning of that. So the physical meaning of that is that if I calculate this number and I assume that I have that much DC voltage, it will give me same power as this AC voltage. So the effective means, what is the effect of that? If, for example, I have a current which is like that and its value is 10 amperes, maximum, when I find the RMS value, for example, if you have a sine wave, the RMS value for any sine wave is equal to peak value over root 2. Like you expand this equation, the sine square is like 1 minus cosine 2t, then you take the integration, and then when you simplify it, you will find that the RMS voltage will be equal to peak voltage by root 2. So for example, if I had, or RMS current is peak current by root 2. Same, for current, for voltage, no problem. So suppose I had a current of 10 ampere, like that, then its RMS value will be 10 by root 2. So the power which this current will supply to, say, 1 ohm resistor will be equal to like 50 watts. See, this square into 1. So this is why RMS value is very important in all the AC calculations. Whenever you say voltage is 220, for example, your house voltage is 220. 220 is the RMS value. It is not the peak value. So actually the voltage will vary, go from 0 to actually 220 into root 2, then come back to 0, then minus 220 into root 2, then comes back to 0, like cyclic, sinusoidal. But the RMS value will be 220. Or I say that this heater takes 10 amperes, that means RMS current is 10 ampere. It's not the peak value. So always when we talk about AC systems, our voltage is RMS voltage. Our current is RMS current. And the meaning of RMS, I think you understand now, it is effective. Like what effect it has. If, for example, suppose this current, let's say this is 50 ampere, is flowing into 10 ohm resistor. What is the effect of this current? So you will say the peak current is 50, the RMS value is 50 by root 2, and the power is I square into R. So this one will basically give you 2500 into 10 by 2. So it will be so many watts. So this is the meaning of like RMS value or effective value, and waveform, the frequency and the angle. Clear? You will get this. Of course, how we generate this is an interesting thing. If I want to produce this voltage, how will I produce this voltage? Just imagine that this side, there is a magnet. So that is north pole and this is south pole. So in this room, magnetism is going like that. And then I take a coil, like take a wire, which goes like that, then like that, then like that. So I have a wire, and I start rotating it. If I rotate this wire, when I make one rotation, I'll get one cycle of this voltage. Because what happens is that, suppose the magnetism is going like that, in this direction. Sorry, it's no. Magnetism is going like that, and your coil is, say, rotating like that. It is going like that. When it is here, it is going parallel to the lines. So it is not cutting any line. So you'll get a zero voltage. When it is here, again at that instant it is not cutting any line, zero voltage. When it is here, it is cutting the maximum line, so you'll get peak voltage. When it is here, it will get negative peak. So actually when you make one cycle, one rotation, you will get one cycle of the voltage. So generally in generators, our like AC generators, what we have is we actually have a coil which is fixed, and we have a magnet which we rotate. So we rotate the magnet and it will give you the voltage. And we get a voltage which is of this type. So this is a single phase. So you can say that I have a generator and the voltage here is equal to, let's say, A dash. This point is A, this point is A dash, is equal to Vm sine of omega t. So this is voltage. And the other characteristics I already explained it to you. Now the question is, what is a three-phase? What is the meaning of three-phase? Now suppose another person has a generator, he brings another generator, which gives us a voltage between, let's say, B dash and B, and the voltage is equal to Vm sine of omega t minus 120 degrees. So we have a voltage. The voltage has same value, Vm, has same frequency, omega, same wave, sine. But the angle of this was 0, and the angle of this is minus 120 degrees. So you have a second voltage, which is like Vm sine of omega t, but with a different angle. Okay? Then suppose I have a third voltage, between C and C dash, and this voltage is Vm sine of omega t, say plus 120 degrees. That was minus 120, this is plus 120. So if you try to sketch these voltages on the same graph, you will have something like that. Let's say this 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. So first is maximum here, then 0, then maximum here, and this is VA dash. Its value is Vm, this is Vm. The second one is minus 120 degrees. So that means basically, here, here, here. So it will be like this. This is the second voltage, this one. The third is plus 120 degrees. So it will be basically, it will be like this. This is your voltage A. This is your voltage B. And this is voltage C. So you have three voltages. Their maximum value same. Their RMS value same. Their frequency same. Their waveform same. The only difference is they have different angles. One has 0 angle, the second is displaced by minus 120, and the third is displaced by plus 120. These are called three-phase voltages. So these are three-phase voltages. This is phase A voltage. This is phase B voltage. And this is phase C voltage. So when we say three-phase system, it is actually a system which has three voltages. Phase A voltage, phase B voltage, phase C voltage. All the voltages are sinusoidal. They all have 60 Hz frequency. And they all have same value. But their phase angle is different. The phase angle is such that, for example, if you have this one, you can say this is Vm angle 0. Like if you try to express it as a vector or as a phasor. And this one you express as Vm angle minus 120. And this one you express as Vn angle plus 120. These are peak value phasors. You can also get RMS value phasors, which will have similar things. Now, if you try to look at all three of them together, this is A, this is B, and this is C. Actually, this angle is 120, this angle is 120, and this angle is 120. This arrangement has several advantages, several benefits, due to which we actually use this type of system in power generation, transmission, and distribution. Okay. So first, you understand the meaning of three phases. That is, it's basically you have three voltages. They are all same waveform, sinusoidal. They have same maximum value. They have same RMS value. They have same frequency, but the phase angles of them are different. When one is maximum here, the other will be maximum after 120 degrees, and the third will be maximum after another 120 degrees. So if you try to plot their phasors, you'll have three vectors which are 120 degrees displaced with respect to one another. Okay? Usually we produce these voltages so that this and this and this, they are equal. When they are equal, we say our system is balanced. So in a balanced system, you have equal voltages. If the voltages are not equal, then the system is unbalanced. So you have balanced system and unbalanced system. If the voltages are same, balanced. It's not only the voltages are same, the angle is also 120. If angle is not 120, difference between them, it's unbalanced. Anyway, we are not really going into balance or unbalance, but just generally the idea of a balance. Okay? Now, of course, you have three generators. If, for example, I want to give connection to people, I will have a wire and I'll give to one house. Or one room in your house, for example. I'll have another set of wires and give connection to another person. I'll have another set of wires and give connection to another person. So you have three sources, and if you want to supply three lamps, you are taking two wires from each one of them, which means basically 6 wires. So if I had a single phase system, I will be having one single phase system for your house, one single phase system for your brother's house. This is your house, your brother's house, your other brother's house, for example. Like 3 houses close to one another. And 2 wires like that. Actually, in 3-phase systems, we can make a trick. What we can do is, we can actually join this point and this point and this point together. Because this is taking current and bringing back. This is taking current and bringing back. This is taking current and bringing back. So you say that, why don't we, connect them in such a manner that we can, for example, I can connect this point and this point together with wire. Just simple. Like connect them together. Here and here. If you do that, actually you will have this type of arrangement. I'm going to raise this. So, for example, I'll have VAA dash. I have VBB dash. And I have VCC dash. Plus minus, plus minus. Plus. This is point A, this is point B, this is point C. Now all these three common, we call it neutral point. So the common point between these 3 generators is the neutral point, and the common wire is the neutral wire. So in a 3-phase, and this one, how it looks like if you look at the shape is like that. Or somebody can draw it like that. So it has a name, it's called Y connection or star connection. So 3-phase can be connected in star or Y. They have same meaning. That means one point of each generator you are putting it together to make the neutral, and the other live points are A, B, C. You say, oh, so what is the benefit? Why you are doing that? Okay. Because these are 3 phases, so the current, for example, I have load here. And excuse me, I have load here. If I want to keep my system balanced, I must have same load, same impedance here, same impedance here, same impedance here. So I have same voltage, same impedance. As a result, this one will give me current, which is say I angle 0, if I put a resistance here. And this one will give me current, which is I angle minus 1. And this one will be plus 120, and this one will be minus. So I have 3 currents. Again, they are same magnitude, waveform same, etc. The angles are like different. Okay. Now the important point is, see, what will be current here? This is the neutral current. Can you give me some idea what will be neutral current? Will be IA plus IB plus IC. It is the current of A phase plus current of B phase plus current of C phase. Okay? Which basically means it is I angle 0 plus I angle minus 120 plus I angle plus 1. Actually, if you try to take any value of I and calculate it, it will be big 0. So actually, the total current from all this is equal to 0. So if you like, you don't have to use this wire. You can have only 3 wires and connect them together, and that will be fine. If I had single phase system, I had 6 wires. Here I have 3 wires. So I'm saving on the transmission wires. There is a saving in the wires. When the current goes here, there is some losses in this wire and in this wire. Losses in this wire and this wire. Losses in this wire and this wire. Here I have losses only in 3 wires. So I save in losses. When the current flows here, there is a voltage drop in this wire and this wire, so I have less voltage here. Voltage drop here and here, less voltage. In this case, only voltage drop in one wire. So I have better voltage at the load. So as a result, in a 3-phase system, you need less wires to carry the power from the generation to the load. So you save on material. You have less losses. And you also have less voltage drops. You have a better voltage profile. There are some other benefits also. But this is basically a system which is like, a Y-connected system. This is a Y-connected system. Your generator is Y, your load is Y. You can also have generator like that. And load like this. For example, you can put one resistor like that, one resistor like that, one resistor like that. So your generator is Y, your load is delta. So delta. So again, in this case, it will basically, you'll have current here, you'll current here, current here. It will be working perfectly nicely. You don't need any other wire. Okay. I can also have the generator connected in this fashion. Like I can connect the generator like a delta and load like this. So actually my generator can be Y and load can be Y. Generator can be Y, load can be delta. Generator can be delta, load can be Y, and generator can be delta and load can be delta. So in a 3-phase systems, you can connect your generator in Y or delta. And you can connect your load in Y and delta. These are both possible, and we use all of them. So I gave you some benefits of a 3-phase system. That is, you need less number of wires, you have less power losses, you have less voltage drop. There are some other benefits in addition to that. Okay, let's try to explain one. For example, if I can now get rid of this one. And let's say I have a generator. This is A, B, C, and neutral. This is VA to neutral. This is VB to neutral. And this is VC to neutral. Like point A dash, B dash, C dash, they are joined together and we call them neutral. So it's a neutral point. This one, the voltage is say V angle 0. This voltage is V angle minus 120. And this voltage is V angle plus 120. Now actually, if you take a voltmeter and measure the voltage here from A to B or B to C or C to A, you'll get 3 equal values. You'll get 3 voltages which have same value. And if you take the same voltmeter and measure from A to neutral and B to neutral and C to neutral, you will also get 3 equal voltages. However, the voltage which you get here is different than voltage which you get from here to there. This voltage from A to B or B to C or C to A is basically voltage from one line to the other line. From one line, line A to line B, from line B to line C, or from line C to line A. So these are called line voltages. So you have three line voltages between line AB, line VC, and line CA. Okay? Also, there is a voltage between A to N, between B to N, and between C to N. These are called phase voltages. So there is phase A voltage, phase B voltage, phase C voltage. Phase A voltage means voltage from point A to neutral. Phase B voltage means voltage from point B to neutral. And phase C voltage means voltage from point C to neutral. Line voltage AB is voltage between line A and line B, or line B and line C, or line C and line A. Okay? You say, so what? Why you are making things so complicated? Why we have so many voltages, and what is the benefit of that? Now let's try to see, actually there is a relationship between this voltage and this voltage. And that is an important part for electrical engineers to understand what is the link between the phase voltage and the line voltage. For example, let's say I have voltage here, VAB. I want to see, if I know VAN, VBN, what will be VAB? So, for example, what is VAB equal to? Can you help? This is, you can do perfectly well from 201. You don't need any like you see, if you go like that, you can try to see what is VAB equal to. You can go like here, voltage rise VAB. You go from here to here, there is a drop of VAN. You go from here to here, there is a rise of VBN. Equal to the Kirchhoff voltage. Like just going like in this form. As a result, you have VAB equal to VAN minus VBN. Similarly, VBC will be equal to VBN minus VCN, and VCA will be equal to VCN minus VA. Okay. Now let's try to give you some meaning of these things. Suppose this was 100 angle 0. What will be this value? Will be 100 angle minus 120, and this will be 100 angle plus 120, and this one will be equal to 100 angle 0 minus 100 angle minus 1. If you use a calculator and try to simplify this one, you will find that this thing is equal to 173.2 and the angle is 30 degrees. If you're not sure, for example, this is 100 plus J0. And this one is minus 100 cosine of minus 120 is minus 50, and minus J 86.6. Like I'm just changing these polar form into a triangular form. If you simplify it, it becomes 150 plus J 86.6, which is equal to 173.2. Actually, what is 173.2? This is actually root 3 times 100. and angle is plus 30. So your VAB will be 100 into root 3 angle 30. This VBC, for example, I'll put it here. This is root 3 into 100 angle 30. This will be root 3 into 100. This angle was minus 120, so minus 120 plus 30. And this will be root 3 into 100. Angle will be, this is plus 120, so 120 plus 30. So actually, your line voltage is equal to root 3 times the phase voltage. The magnitude of the line voltage is root 3 times the phase voltage magnitude. Angle of the line voltage is phase voltage angle plus 30 degrees. Forget the angle, the voltage magnitude is important. Now, in your house, you may say, I have 220 volts and I have 110 volt in our house available. Actually, you don't have 110 in your house. You have 220 and 127. If your house was built earlier, old, like where I'm living, it's old wiring. It has 127 and 220. If your house is a new construction built recently, it will have 380 and 220. So your house has two voltages. You can go and check yourself. Like you'll have some plugs with higher voltage, other plugs with lower voltage. This one is phase voltage and this is the line. This is the phase voltage and this is the line. Now, you say, well, okay, we have two voltages, but what is the use? What is the benefit? So in your house, all the loads which need more power, you will connect them here or here. Air conditioners, heaters, water heaters, ovens, like all the things which need large power, because power is voltage into current. So if you use a higher voltage, you will need smaller current. If you need smaller current, wires will be small, losses will be small, so it is more efficient. Okay? And the lower power loads, you will connect lamps, small electronic devices, you will connect. So we have basically line voltage and a phase voltage. In our houses, our system is like that. Like we have three phases and the neutrals. We have 4 wires coming to your house from the Saudi Electricity Company. One wire will have phase A, phase B, phase C, and neutral. Now, how you use your house, what you do is, you'll connect all the lights from one room to phase A. Then the lights in the next room, phase B. Then the lights in the third room to phase C. So, balanced. So you have same load on phase A, phase B, phase C. You connect one AC from A to B. You will connect the next AC from B to C. You will connect next AC from C to A. Balanced. So this way, we try to balance the house, the load in our houses, and we have a 3-phase system. And this is a Y-connected arrangement. Clear? So in a 3-phase system, you have phase voltage and you have line voltage. If you have to figure out what is the meaning of them, line voltage is you take a voltmeter and measure from one line terminal to the other terminal, from this one to this one, and from this one to this one. This will give you the line voltage. If you want to measure the phase voltage, you will take from this terminal to the neutral, from this terminal to the neutral, from this terminal to the neutral. Okay? It's clear? Also, this is a Y connection. And actually there is a current here and there is a current here. This current is called phase current. It is flowing in the phase. And this current is called line current. It is going out from the line. Of course, in this case, this and this current is same. Because by Kirchhoff's current law, if you write equation at this node, this must be equal to that. So in a Y connection arrangement, our Y connection, the line voltage is root 3 times phase voltage. And the line current is equal to phase current. Clear? Now there is another arrangement, and in that arrangement we do like this. For example, this is 1, this is 2nd, and this is 3rd. Let's say this is A dash, this is B dash, and this is C dash. And then take up like that. This is called delta. So you can predict it in the delta arrangement. The generator can be connected in the delta arrangement. Of course, your VA is same, like this is V angle 0, and this is V angle minus 120, and this is V angle plus 120. If you take a voltmeter and measure from here to here, this will be line voltage. This is A, this is B, and this is C. Like this is from A to C, B to C, and A to B. So if you measure here, line voltage. If you measure here, phase voltage. For example, if I put a voltmeter here, and then here and here, will I get same values or different? Same values. Because, so actually in delta connection, line voltage is same as phase. So no difference. So you have only one set of voltages. You don't have two different voltages available in that. It's voltage from A to B, B to C, C to D. Okay. Now, let's say there is a current going like that, IA. There is current going like that, IB. Let's say this is I going from C to A. This is I going from A to B. And this is I going from B to C. So you have current flowing here, current flowing here, current flowing here. These are called phase currents because this is phase current, phase A current, this is phase B current, this is phase C current. Current flowing in different phases. Also there is a current going here, and there is current going here, and there is current going here. These are going out in the lines. These are line currents. So you have line currents and you have phase currents. In this case, actually, if you want to find this, you write an equation here, like this is equal to this plus this. So from there, you'll find this is equal to this minus this. And this is equal to this minus this, and this is equal to this minus this. So actually, your line current, if you make the same analysis, you'll find that it is equal to root 3 times the phase current. So in one configuration, the line voltage is root 3 times the phase voltage. In the second configuration, the line current is root 3 times the phase current. In one case, the line voltage is same as phase voltage. In the second case, the line current is same as the phase current. So, there is a difference between, you can see, here the voltage has this relationship, here the current has that relationship. Okay? Then is that if you have a three-phase system, how do you find the power? because you are interested to find the power. And for power, of course, you have heard, like in AC systems, there is something called P, there is something called Q, and there is something called S in AC systems. You know what is P? What is P called? Sorry? Real power or active power. It's like watts. Real power. And what is Q called? Reactive power. The units are var. And what is S? Sorry? It is called complex power or apparent power. The units are volt and ampere. Actually, you can write S is equal to P plus 2. I would like to explain you the physical meaning of Q. Because you understand P, I think we explained the P. But Q, most of the people, even most of the engineers will not know what is the physical meaning of Q. He'll give the formula, Q is equal to this, but he will not know what it physically means. First of all, of course, in a single phase system, your P was equal to V RMS, I RMS, cosine of I. This was the angle between voltage and the current, and this is called power factor. The Q was given as V RMS, I RMS, sine of I. And S is V RMS, I RMS. Okay? Now, I explained you earlier that suppose I have a resistance, the voltage is like that, the current is like that, and the power is like that. With time, the average value is equal to V RMS, I RMS. So, about P, I think you understand. Because I defined it also when I defined the RMS value. It's basically, if over one cycle, how much is the average power. Q. The Q actually comes from inductance or capacitance. For example, if I have a voltage like that, in inductance, the current lags the voltage by 90 degrees. The current and voltage are not in phase in the inductance. So, in inductance, if you draw the current, it will be like that. This is V, this is I, and I. If you have inductance like that, if you have a capacitor, it will be like this. It will basically be like that. Anyway, let's just concentrate on inductance. If we try to find power now, we said power is product of voltage and current. So, see, this point has one quantity 0, this point has another quantity 0, this point has one quantity 0, this point has another quantity 0, this point has one quantity 0. So, at all these points, power will be 0. Here, one is positive, the other is negative. So, what will be the answer? Negative. So, actually, the power curve in this part will be like this. 0 here, 0 here, in between will increase and then come back to 0. Here, they are both positive, so it will be like this. Here, one negative, one positive, and here like that. So, you see, the power in case of inductance is like this.
be bigger than that.
Sorry?
T multiplied by I should be bigger than the cube of power.
No. See, like for example, V is 10. I is say 0.1. The answer will be 1. So it depends what is the value of I at that particular point. But I'm saying, just try to concentrate on the shape of this thing. Actually, if you try to find what is the area of this under this curve. Sorry? 0. Because you have positive area equal negative area, positive area equal negative area. So actually, average power in inductance is 0. So what is happening? Actually, inductor is taking current, building up magnetic field and storing energy. Then, it is collapsing the magnetic field and giving that energy back to the system. So you have positive power, it is taking energy to build up its magnetism. You have negative power, the stored energy is going back to the system. Then, building, going back. So, net power, 0. However, power is flowing to the inductor and then going back, flowing to the inductor, going back. Actually, Q is this number. The highest value of power which flows from the generator to the inductance or from inductance to the generator is Q. Physically. So it has a physical effect. Yeah, mathematically you use the proper equations, but basically this is what happens. If you have a capacitor, it has similar behavior. The only difference is, in capacitor, if I plot the power curve, it will be like that. In capacitor, actually current leads the voltage by 90 degree. So, if this is the voltage, the current will be like this. And you can see, like this area will have positive, this area will have negative, then this area will have negative into negative is positive, and then the other will be like negative, like that. So in capacitor, what is happening? First, the capacitor charges up, builds up its static field, and stores energy. Then it starts discharging and gives that energy back to the system. Then charges, discharges. So net energy used is 0. And again, this is the reactive power. Actually, if you look at capacitor and inductor, they are opposite to one another. Inductor is taking power, capacitor is giving. Capacitor is taking power, inductor is giving. So we make use of this thing to design power factor improvement devices. We actually try to improve the power factor in the system. If we have inductive load, we put some capacitors there. Or if we have capacitor thing, we put some inductors there. This is the idea of compensation and some of the other topics like that. Okay? So you understand the meaning of P and Q and things like that. Okay? Now, of course, we are always interested to find power, and we said that the power in a single phase is like that. The question is how you find power in 3 phases. So actually, the power in phase 1 and phase 2 and phase 3 will be same. So the power in a 3-phase system will be 3 times the power of 1 phase. Similarly, Q will be 3 times Q of 1 phase, S will be 3 times S of 1 phase. Because 3 phases are similar. Okay? So we get actually some other equations for that. How you get those equations? Let's try to. Let's say that we have P 3-phase is 3 times P of 1 phase. Of course, what is P of 1 phase? it is equal to phase voltage times the phase current times the cosine of. For one phase, you have a phase voltage, you have phase current, and you have the power factor. So P will be like that, into 3. Now look, if I have Y connection, I can write this thing as this one, root 3 Vp Ip cosine. Sorry, this is P3 phase. Actually, I change this 3 into root 3 times root 3. Of course, this root 3 times Vp is V line. So I make it V line. And Ip is equal to I line. I make it I line. So I get the formula for 3 phase, which is equal to root 3 line voltage into line current into cosine. So this is the typical formula which you use for 3-phase system. That power is equal to, I will write it here. See, like P 3-phase is root 3 V line I line for Y system. If it is a delta system, same thing, because what you will do, you say that, okay, in a delta system, root 3 times Ip is equal to I line. And so it will basically, like for a delta system or for a Y system, you have same equation, and this is for both, for Y and delta. You take the line voltage, you take the line current, and then root 3 into line voltage into line current into power factor is P. Similarly, Q is root 3 line voltage, line current, sine of for both. And S 3-phase is root 3 line voltage. In 3-phase system, when you say voltage, usually you mean the line voltage. And when you say the current, you mean line current. So I say that I have a 3-phase system which has 200 volts and 10 amperes. So 200 volt is the line voltage and 10 ampere is the line current with power factor. Okay? So these are the equations for P and Q. So the important thing in 3-phase circuits is, number one, what is the meaning of phase voltage? What is the meaning of line voltage? What are the 3 phases? Then, what is the equation for power in a 3-phase system? If it is a Y connected, what is the relationship between line voltage and phase voltage? If it is delta connected, what is the relationship between line voltage and phase voltage? And like that. And these are, I've given you all the main equations, but I've not given you some key things from why 3-phase system actually has some other benefits as well. So let me first of all give you like how you produce 3-phase voltages. Actually, if I have a single phase generator, I'll have a part which is stationary. I have fixed it on the floor, and I have a coil which goes like that. It's basically going like that, like that. You can imagine that. This is this thing which you are seeing, made from iron. I have a wire. I take the wire, goes like that, like that. Actually, I make a coil. Then end, I have one end here and one end here. This end is A and this end is A dash. Let's say A dash. And inside, I'll have a magnet. This is north pole and this is south pole. and I rotate this thing like that. When I do that, I'll get a voltage VAA dash is equal to Vm sine of omega. The omega will depend on the speed at which I'm rotating it. If I rotate it at 60 times in 1 second, I'll get 60 hertz. If I rotate it at 50 times in 1 second, I'll get 50 hertz. It's clear? So this is a single phase generator. If I want to make a 3-phase generator, actually I can use the same thing. What I do is, I'll put a coil, this is here, so I'll go 120 degrees and I'll put a coil here, BB dash. So AA dash is here, I go 120 degrees and put another coil BB dash. And then go another 120 degrees and put a coil CC dash. So the same machine, same iron, same everything, same magnet, I have actually put 3 coils. One coil gave me voltage AA dash, the second coil gave me voltage BB dash, and third coil gave me voltage CC dash. And because I've arranged them 120 degrees to one another, so the voltages which I get, one is displaced from the other by 120 degrees. So to make the generator a 3-phase generator is easier, takes less money. Because if I make 3 single-phase generators, I'll need to have this one part iron for each one of them. Here, if I have 3-phase, I use same set of iron for all 3 phases. So it is cheaper. Okay. Similarly, if I want to make a transformer, if I want to make a single-phase transformer, at least I will need an iron like that. Minimum. If I want to have a 3-phase transformer, I will just have like that. I just have one more leg. I put 1 phase here, 2nd phase here, and 3rd phase here. So I save on iron. I save on material. So 3-phase generators, 3-phase transformers, 3-phase motors are cheaper to make than if you make 3 single-phase units of the same rating. See, for example, if I make a generator of 10 kVA and then another one of 10 kVA and another one of 10 kVA, I have a total of 30 kVA. If I make a 3-phase generator of 30 kVA, its cost will be less than 3 generators of 10 kVA each of single phase. Same for transformers, same for motors. Transmission, I already explained to you that instead of 6 wires, you have 3 wires. It's clear? So 3-phase is more economical for generation, for transformation, voltage transformation in transformers, and for use in motors. Your 3-phase motors are much economical than single-phase motors. One last thing, that 3-phase, if you have a single-phase machine, I already explained to you that if you have a single phase, you will have, let me just show you a single phase. I have voltage and I have current. And if I try to sketch the power, you find power like that. So you see, if you try to think like the generation, you have to actually turn this shaft. You have tried to rotate this shaft. You need to give a torque to this shaft so that it is rotated by some external force. And that torque is not constant, it is changing like that. Of course, you cannot change torque like that. Once you have something, it will keep on driving like that. So when you have arrangement like that, it creates vibrations in the shaft. Because actually the torque required is this much. But you are having something which is not exactly same value, sometimes less, sometimes more. As a result, it is shaky. It vibrates. Now suppose I have a 3-phase system. In 3-phase system, of course, I'll have the power from phase A, power from phase B, power from phase C. So the shaft will have a torque which is from all of them together, from A, from B, from C. Okay, and how they are like this. I will just explain it and then let me just try to draw the diagram. See, for example, this is 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. This is 360. This is 180. This is 90. This is 270. The phase A power is like that. It will be maximum here, so it will be like this one. And then this is the phase A power. Phase B is displaced by 120 degrees. So that power will basically will be like that. Sorry. This is B, if it was a resistance. And then if you try to look at the C, 1, 2, 3, 4, 120, 1, 2, 3, 4, another 120. Actually, if you try to add these three curves at every point, like you add this purple plus blue plus white, at every point you'll find that it is constant. At any point when you add it, it's constant. So if you are driving a three-phase generator, there is a constant torque, there are no light vibrations. So your source is like, it is very nicely. So this is the reason that worldwide, every power system is actually a three-phase system. The power is generated like that, it is transferred like that, it is distributed like that. We have the option in our homes, we have two different voltages available. So you can have the line voltage, you have the phase voltage. If you need more power, you connect it to line voltage. If you need less power, you connect it to phase voltage. And we can balance the arrangement, that is, one phase is supplying this AC, second phase is supplying this AC, third phase is supplying this AC, or this room, this room, this room. So like that. This is the basic idea of the three-phase circuits. Okay? Now generally, when you want to solve the problems involving three-phase, it becomes a simple matter. Because we know that phase A, phase B, phase C has same voltages. Difference is only phase angles. Phase A, phase B, phase C has same currents. The difference is only the angles. Power, same. Reactive power, same. So all we do is, when we want to solve the problem, for example, just imagine that I have this simple system. Like I have a three-phase generator. I have three lines and neutral, let's say A, B, C, and neutral, a transmission line, and I have three-phase loads. And you want to find out how you will solve the problem. So basically, all you do is you will draw the circuit for one phase of the generator. This is phase A and this is the neutral, and you will take the impedance of this line this is impedance of line A, and you will take the impedance of the load phase A, and this is line A, and you solve it. You get the answer for phase A. you get the voltage here, you get the current here. So this current is phase A current, phase B current will be same with the displaced angle by 120. Phase C current will be same with displaced by 120. And the voltage, load voltage, you find from there, current into this resistance will be the load. So phase A voltage same, phase B just angle shifted, phase C just angle shifted. If you want to find the line value, you know this value multiplied by √3, you get the line values. So power, find power of this, multiply by 3, you get power of 3. Find power factor, find losses, find everything. So it is basically like, a simple method to solve the problems of three-phase. Provided it is balanced. If it is not balanced, then you cannot make this arrangement. Because then you will have another voltage and another line and another load, and then you will have another voltage and another line and another load. So then you need to use loop and mesh and node and whatnot. It becomes quite complicated. So usually unbalanced things we don't teach unless you are specializing in power, and only there when there is some problem in the system. Because normally we make our system that it is balanced. But sometimes there are problems like, you have a breakdown of something or you have some fault, so it becomes unbalanced. So at that time, you can solve it by, there are methods for that. Okay? So if I just close this session, I'll give you time to ask questions. So basically, three-phase system is nothing. It's like, it is a machine which will give you 3 voltages instead of 1 voltage. The 3 voltages have same wave shape, have same magnitude, peak value, RMS value, have same frequency, but they are shifted by 120 degrees each. One like that, one like that, one like that. Actually, if you have 3 forces like that, their sum is 0. When you have 3 forces like, if one person is pulling like that, another is pulling like that, and third is pulling like that, actually 0 force. The net force is 0. So when you have 3 vectors at 120 degree displaced, it is 0. That means the sum of the 3 current is 0. So there is no, actually what is happening, current is going from here and returning from here and there, going from here and there, returning from here, because instantaneously, like if you, I just give me one second and then you will understand the point. Like for example, see you have Vm sine of omega t. You have Vm sine of omega t, say plus 120. And you have Vm sine of omega t minus 120. These are three-phase things. Can be voltage, can be current, doesn't matter. Okay? Now just imagine that suppose I'll just give you 3 points. I'll take value of omega t and we try to find what is the result. For example, we say omega t equal to 0. So this one will be 0. Vm sine of 0 will be 0. This one will be Vm sine of 120. Right? So, this is √3 by 2. And this is Vm sine of minus 120. It will be minus √3 by 2. Yeah. If you add these three together, what you get? 0. Now let's say omega t is not 0. Let's say omega t is say 90 degrees. I'll just do like, if it is 90, this is Vm. This is sine of 120, 120 plus 90, sine of 210 degrees. So you have sine of 210. This is minus half. And this one is sine of minus 30, because 90 minus 120 is minus 30. So you have sine of this is also minus half. See what is the sum? 0. Similarly, take any value of the angle. At that instant, the sum of these three things will be 0. As a result, the current in a three-phase system, the return current is 0. And this property is used to design. So I think I gave a general idea that it is easier to make a generator which is three-phase. That generator is more robust, less cost, more economical. The transmission line will have less conductors, because if you see around Riyadh, you see lines with only three wires. Actually, you see 6 wires, but these are 2 different circuits, like a road with 2 lanes, 2 parallel roads basically. So you have 3 wires from phase A and 3 wires, A, B, C, one circuit, and then A, B, C, another one circuit. So you have actually on same set of tower, you have 2 transmission lines. Okay, and if you were using single phase, you know that if you have to connect a computer, you need 2 wires. If you have to connect second computer, 2 wires. Third computer, 2 wires. But if you connect these computers in a star manner, you just need to bring 1 wire from there, 1 from there, 1 from there, and the other side of 3, the connections, you can join them together and make them like that. So you save on the wire, you save on the cost of losses, and many factors. Now you are free to ask questions. I try to answer questions. If you have anything, I hope you got something from this one. If not, I can try to
okay. Between the 3 pages should be what you, or could I choose any angle?
No, see, angle, the difference between them should be, because you have 360 and you divide it by 3, should be 120. But for example, one voltage can have angle V, angle say 30. And the second voltage then will be V angle 150. And the third voltage will be V angle 270. Like the difference between the two should be 120. It can have any angle value, but the difference between the 2 voltages should be 120. Okay?
Yes, and that is what.
Thank you very much.
Thank you very much.